How's it going, guys? In this video we're going to go over pressure and solubility, and more specifically Henry's law. So let's define that. The amount of dissolved gas in a liquid is proportional to its partial pressure above the liquid. So there's a bunch of different formulas you can use to calculate this, but essentially if the pressure increases above the surface, whatever we're measuring is going to be encouraged to enter that liquid. Its solubility is going to increase. So one more common application of this Henry's law is soda making process. So because the high pressure and low temperature maximize gas absorption, that's exactly what they try to use to generate soda, to create it. Basically, the manufacturers condense, they add the CO2, they condense the chamber to increase the pressure, and then they greatly lower the temperature. So most, like Coca-Cola and all that, they're made between like 2 and 5 degrees Celsius. So anyway, with that covered, we're just going to jump into the first problem here. Okay, cool. So how many grams of CO2 are dissolved in a 2-liter soda bottle if the manufacturer uses 3.6 atm for the bottling process at 4 degrees at 4 degrees Celsius? Assume the KH of CO2 in water is 4 degrees Celsius, and at 4 degrees Celsius is 29.76 atm. So with that, that's going to be our first problem. Let's just jump in. Where do we start with something like that? This is how I started off. We'll go with C equals, because we're looking at all these formulas here, we can rearrange one to get C equals P over KH. And then we can kind of just plug things in that we have. We have 3.6 atm. That's the pressure that this particular company, the manufacturer, uses. Now we have our KH, which we're given, is 29.76 atm. And we're just going to divide that to get our C. And what we're going to get is 0.12 moles per liter. And then we know here we have they're asking for 2 liters. So we're just going to multiply that by 2 for the 2 liters, which equals 0.24 moles of CO2. Now we take 0.24 moles of CO2, and we're going to just put that into grams of CO2 because it says how many grams of CO2 are dissolved. So from there, we're going to just multiply 1 mole of CO2 is equal to, we're going to use the molar mass, which is 44.01 grams of CO2. And what are we going to get? Okay, we got 10.5624 grams of CO2. And we can round that off. We can say, okay, there are 10.56 grams of CO2 in a 2-liter soda bottle. In case anyone's tracking how many grams of carbon dioxide they consume. Okay, so next we're going to jump into probably the other most common type of, I don't know what you'd call it, a real-world example of the application of Henry's law, and that is going to be, let me see if I have room for this, scuba diving. So a scuba diver is breathing air which is 78% nitrogen by mass. If the diver takes a breath at the depth where the pressure is 3.85 atm and 2.15 atm, what will the diver's blood nitrogen concentration be at each depth? Solubility of nitrogen at 37 degrees Celsius, which is body temperature, and atm, and at 1 atm is 6.2 times 10 to the negative 4th. So essentially what we have here is, this is sea level, theoretically this is sea level, so 1 atm, and then the diver goes down, we have the 3.85, and then we have 2.15 on, I guess about, approximately part of the way back up to the surface. And we're going to assume that as soon as the diver takes this breath, it's like pretty much instantly those nitrogen levels are going to be based only on that breath. So it's a little bit of a stretch in terms of actual logic, but here's what we're going to do to solve this. We have K equals C of N2, which is the nitrogen is going to be diatomic. That's another like tricky one. To make an already complex problem even more tricky, they're going to have it be diatomic. So if you missed that, then you'd be, might run into some issues there. 6.2 times 10 to the negative 4, which is what we're given. And that will be divided by 1.00 ATM. We're starting from the surface. Now we have just the same, 6.2 times 10 to the negative 4th m per ATM. So we have our kind of like our baseline. And now what we can do is we can go for the P of N2, which is going to equal X of N2 times P total. So what that's going to equal is, we have the percentage, so we're going to put that into a decimal, 0.78 for 78%. And then we're going to do of 3.85 ATM, because that's what we have down here. And now what we're going to get as a result is 3.003 ATM. Now our C of N2 is going to be, let me scoot that down, C of N2 is going to be equal to our K of P N2 6.2 times 10 to the negative 4 m over ATM times 3.003 ATM. So now we're going to just multiply this across, the 6.2 times 10 to the negative 4th times 3.003. For the C of N2, we're going to get 1.86 times 10 to the negative 3. And then we're just going to do the next one. P of N2 equals X of N2 times P total. We're going to get, see if I can scoot that down a little further. We're going to get, again, the 0.78 based on the percentage that we have up there. Then we have our other 2.15, our other pressure when the diver is returning to the surface. So from here we're going to do, and get 1.677 ATM. Now we're going to use that for the C of N2 at the middle depth. K of P N2 equals 6.2 times 10 to the negative 4th m over ATM. And from there we're going to multiply that by 1.677 ATM. And what do we get? Going to get 1.04 times 10 to the negative 3 molar. And that makes sense. So let's just double check back to what the question's asking. What will the diver's blood nitrogen concentration be at each depth? So we already have, this is what it is at the surface or at sea level, 1 ATM. And then from there, we're going to have the lowest depth that the diver goes to, which is 3.85 ATM, and we get 1.86. And then in the middle, on the diver's way back up to the surface, we have 1.04 times 10 to the negative 3. And yeah. So again, this is that kind of example about the application of Henry's law. I think, yeah, scuba diver. Whenever I think of Henry's law, just think of scuba divers and soda. So yeah, hopefully this is useful to someone.